So true versus quasi-experimental designs. The major difference between true experiments and quasi-experiments from the first week of class is the degree of control the researcher has over the study design. So more control over the design tends to result in better research validity, maybe not external validity, but the other types, and greater accuracy of your research conclusions. So internal validity and construct validity for causal conclusions is much higher with a true experimental design. Statistical validity is higher under controlled conditions because there's less noise, less sort of random error, but external validity tends to be lower under tightly controlled conditions. So true experiments provide much more control over the study design than quasi-experiments, and therefore tend to lead to more accurate and unambiguous, that means not confounded, conclusions about the causal effects of independent variables on dependent variables. Now, quasi-experiments aren't just like lame. They can lead to accurate conclusions about causal effects if the alternative explanations for differences you find are ruled out. So you do a good job of that anyway, but they're generally more ambiguous and more likely to be confounded than true experiments. So what are some properties of quasi-experimental designs? Well, they may have actively manipulated IVs. So, you can actually determine what the levels of things are, but still people might pick them, right? Self-select into them rather than random assignment. So most of the time you're just measuring things in quasi-experimental designs. You're not actively manipulating them. So controlling the timing and the content of the IV conditions is important for your construct validity, and that's one of the things you don't have as much control over in quasi-experimental designs. So they're useful though when you can't ethically or practically manipulate the independent variable. So they may have a controller comparison group, or they may have a pre-post dependent variable measurement as a basis for comparison. So again, they can have these things to the extent they do. They're better quasi-experimental designs. If you don't have a control group, it's difficult to rule out various threats to internal validity when we were talking about that a couple weeks ago. So one of the true sort of things of quasi-experimental designs is they never have random assignment to independent variable levels. So that's one of the ways you can tell is this a true experiment or quasi-experiment. Remember that first week, the IBDB assignment. If you could randomly assign it could be a true experiment. So the groups may not be comparable. There's self-selection bias. That is like the major sort of bias in quasi-experimental designs is people pick their conditions and you just measure them usually. What group are they in? So there's generally no or poor control for extraneous variables, that is other sources of confounding. Another big problem with quasi-experimental designs, which self-selection is one of those problems. So it's difficult for you to ensure that the only difference between the groups is the IV when you're just selecting people how they are, like people who have insurance or not, that kind of thing. Well, there's plenty of other things that vary along with having insurance that may be important and may explain the findings you get. So how do you know if you've got a quasi-experiment versus a correlational study? It's pretty hard. So the designation of whether it's correlational or quasi-experimental design, it's kind of arbitrary, but there are some rules here I came up with to help you figure it out. So if a study does not have a specified IV, right, it's just looking at the relationship between two variables or regression or something, it's correlational. If a study has a specified IV that's manipulated by the researcher, it's clearly quasi-experimental. If a study has a specified IV, but the IV is not manipulated by the researcher, so it's just naturally occurring conditions, you really got to look at what statistic was used to analyze the data, and that helps you determine what the research design is. So if you use correlation or regression, it's correlational design. If you analyze counts, means, or rates using like chi-square or t-test or ANOVA, something like that, it's quasi-experimental design. So if a study fits a design we cover in this section, it's also quasi-experimental. So hopefully that's useful. So there are 8 major types of quasi-experimental designs. We're going to talk about them all. There's the one group post-test only. It's also known as the one-shot case study. The post-test only design with a non-equivalent control group, the one group pretest post-test design, the multiple levels pretest post-test design, the untreated control group pretest-posttest design, the interrupted time series design, and the multiple interrupted time series design, and finally, the single subject reversal designs. So these are all quasi-experimental designs. So let's talk about the first one. The first one is a one group post-test only design. So you start the sample, somehow you get a sample, and from that sample, you do not randomly assign them, and they become your study group, that whole sample. And you expose them to some sort of treatment or event, and you measure the outcome, right? So the DV is measured for one group after some sort of treatment or event occurs. So for example, after a hospital obtains ultraviolet light equipment, a researcher gathers opinions from staff about how they think its use has affected surgical site infection incidents. So they just kind of go in after a thing happens and ask questions. So, or you go in and ask, what's your opinion of emergency personnel after some sort of disaster occurs? And, shockingly, people are thankful. So another example is late night infomercials where people just say, look, I use this product, it increased my vitality. That's a one-shot case study, and it also happens to be a one-group post-test only design. Yes, after this, it helped me. So opinion research in general tends to be one-group post-test only design. You're just asking people their opinions after a thing happens. What do you think of this, right? So there's no actively manipulated IV. In fact, there's no independent variable at all, right? There's what varies here. You're just getting DV measures after something happens. There's no control or comparison group at all. There's no pre or post, right? It's just post only. You didn't have their opinion about emergency personnel before the disaster happened and compare to how they felt about it afterwards. And there's clearly no random assignment to IV levels. There's no IV. So further, there's no control of other extraneous variables. Like, this design's actually awful. So this is a bad research design. There's really no basis for drawing conclusions under the scientific method. You just know that, hey, this is what people told me after a thing happened, but you don't know if it was caused by it. You don't know if other factors, if anything changed at all, for example. So bad design. The next design is the post-test only design with a non-equivalent control group. So we're going to have a control group here. They're just non-equivalent because we didn't randomly assign. So you start with a sample, and from that sample, there's no random assignment. And you form two groups, A and B, in some non-random way. You let them pick what they want to be in, or you get pre-existing groups that are out there who bought the product, didn't buy the product, whatever it happens to be, but they chose what group they're in. And in the treatment level or experimental group, they had the thing of interest. Then there's a non-treatment or a control group, a group that didn't get the insurance or didn't get the machine or didn't, whatever it is, the thing of interest, you're just collecting them. And you measure the DV. So there is a comparison group here, but there's just a post-only measure. That's why it's called the post-test only design with non-equivalent control group. So you compare two non-randomized groups on a single DV measurement after one experiences the treatment or event or whatever it happens to be, and the other one did not. So, for example, you could compare surgical site incidents for a hospital with ultraviolet light machines to the SSI incidents for another hospital that doesn't have ultraviolet light machines. So possibly you can have an actively manipulated IV. You could work at that hospital and determine what machine they bought, for example. But the control group's kind of poor, right? So one group chose to do a thing, one group did not. What factors affected that choice? They could affect your DV measurements as well. There is no pre-post measure, so for all you know, these two hospitals had different surgical site infection rate differences beforehand. You have no idea. Or the hospital that bought the machine did so because their rates were so bad. So you get no difference afterwards. You wouldn't want to conclude that the ultraviolet lights don't help at all, right? When really it took what was bad and made it normal. So there's no random assignment to levels, and again, there's really bad control of extraneous variables. So this again is a bad research design. There's just too many factors that threaten the validity of your conclusions that you draw. Well, how about number 3? This is the one group pretest posttest design. So we're back to one group, but we're going to test them before and after something happens. So you have a sample. That sample is not randomly assigned. They just are all your study group. And you measure the dependent variable. Then something happens, and you measure the dependent variable again. So you have two measures of the DV, DV1 and DV2. It's a pre-post design, right? And in between, something happens. So it compares one group on DV measurements before and after it has experienced the event or treatment. So for example, you could compare the surgical site infection incidence for a hospital before and after they start using ultraviolet light to reduce infections. There is no actively manipulated IV. The IV here is time, right? You can't manipulate that. So there is no control or comparison group. There is a pre-post measure. So you could say, yes, there was change before and after thing A happened. But can you say that's what caused the change? Who knows? Could be a Hawthorne effect or a novelty effect, right? That caused the change, not really the machine itself. There's no random assignment, and there's really no control of extraneous variables. There's no comparison group to reduce confounding. So again, a really bad design. So there's too many factors that threaten your validity of your causal conclusions. So number 4 is the multiple levels pretest post-test design. It's kind of a variation. It's got a before and after, but there's multiple treatment levels. So you start with the sample, and by whatever means you not randomly assign to groups, you just find out who's in group A and group B, and you measure the DV in the two groups. One group gets whatever the experimental treatment or the changes. The other group gets another experimental treatment or change. Could be B. Can have C, D, and E here, by the way. And then you measure them after. So you've got before and after. Two different groups have some sort of event happen. So you compare multiple non-randomized groups on DV measurements before and after they've experienced different treatments or events. So for example, you could compare the change in surgical site incidence for patients in different wards in a hospital before and after they start using different brands of ultraviolet light equipment. So two different wards, one buys brand A, the other one buys brand B, and you compare their surgical site infection rates before and after each of the wards bought those things. Try to draw conclusions about how effective ultraviolet light is. So you could possibly have an actively manipulated IV. You could determine what machines are in each ward. There is a comparison group, right? You're comparing two different treatments though. There is a pre-post measure, so you could say, look, this thing did change. You still have causal problems inferring the change was due to the treatment itself and not other historical factors, for example. There's no random assignment, and there is poor control of extraneous variables. So this is kind of an okay design. You can draw conclusions about relative effects, like this machine was more effective than that machine, or appears to be, or the change was bigger for the ward that had this machine versus that machine. But you don't actually know if the treatment was effective overall. So there is no touch control group or group that didn't have any treatment here. So you're just talking about relative effects between groups. Number 5 is the untreated control group pretest post-test design. So you do have a comparison group and you do have pre and post. So you start with the sample. There's no random assignment. You end up with two groups. You measure the DV in each of the groups. Then one group gets the treatment or the experimental level of the variable. The other group does not. So you do have a true control group. And then you measure them both after as well. So you got pre-post, one group's treated, one group's not. The only thing that makes this not as great as it could be is you didn't randomly assign to the two groups. So it compares two non-randomized groups on the DV measurements before and after one experienced the treatment or the event of interest. So you could compare, for example, the change in surgical site infection incidence for patients in different wards before and after one starts using UVL equipment as part of its cleaning protocol. The other one does not. So you could talk about change before and after, right? And how you could compare it to what change occurred in the ward that did not buy the machine. And if you get bigger change in the ward that got the machine, it does suggest the machine was, helpful, right? But it could also be novelty effect. So again, you could have possibly manipulated the IV, determined what UVL machine they bought, ultraviolet light. There is a control group. That's good. There is pre-post measurements. You could say, yes, there was definitely change observed, but there's no random assignment, and there's just some control of extraneous variables. The fact that you have a comparison group helps in some ways control for, the hospital management on everyone's case about reducing surgical site infections. Is that the effect? Well, that would affect the control group too, as well as the group that got the ultraviolet light equipment. So it's an okay design. You can draw conclusions about whether the IV had an effect compared to no treatment at all. You can look at, you'd expect maybe bigger change in the treated group versus the control group. So now we're on to something totally different. These are design 6's interrupted time series design. And time series designs look like this. You've got a steady group and you measure them on the DV at some point in time, then you measure them on the DV the next point in time, then you measure them again, keep measuring them, and then eventually something happens. So you've got like 4 measurements here beforehand, something happens, and you measure them afterwards as well. And preferably you got equal measurements before and after. So you've got sort of pre-post design on steroids here, right? With multiple measures before and multiple measures after, but there's no comparison group. So you compare one group across multiple DV measurements before and after it experienced some sort of treatment or event. So for example, you could compare the surgical site infection incidence for a hospital 4 quarters before and 4 quarters after they start using ultraviolet light in addition to their standard cleaning protocol. Or another example, you could compare the number of bicyclists who are hit monthly on J Street in downtown Sacramento before and after they added bicycle lanes. And so what's the flaw in this design? Well, you don't know, again, if you see a change afterwards, was it really due to the event or was it due to historical other things that happened, seasons changed, whatever it happened to be, for example. So there is no actively manipulated IV. Again, the IV here is just time. There's no control or comparison group. You do have pre-post measurements, and those do give you a strong basis for talking about change over time because you got multiple measures before and after. There is no RAM assignment to IV levels. There's really the IV's time. There's no control for extraneous variables, except maybe these things allow you to adjust for trends and seasonality, and that's all you can really control for. So it's considered a pretty bad research design because, even though you can talk about change, you can't really make causal inferences. The change was due to this because you have no control group, right? So next one's better. So design 7 is a multiple interrupted time series design. So you got steady group A and B. You're measuring them multiple times on the DV. Some sort of treatment or special thing happens to one of the groups and does not happen to the other group. And you measure them multiple times afterwards. So you've got multiple pre and post. One group experiences the event, one group does not. And so you compare 2 groups across multiple DV measurements before and after one group experienced the treatment or event. So for example, going back to the surgical site infection stuff, you've got 4 quarters before and 4 quarters after one hospital starts using ultraviolet light as part of their cleaning protocol and the other one does not. So to the extent that there's historical or seasonal sorts of things, you'd see that in the treatment and not, the no treatment group and the treatment group, but you'd expect to see a bigger effect in the treatment group. And that's why this design's a little bit better. So you could go back to that example of comparing bicyclists who were hit on J Street before and after they had bicycle lanes to a similar street where they did not. So you'd want that control or comparison street to be one that was similar in its pre-levels of bicyclists being hit. One group you install bike lane, or one road you install bike lanes, the other one you do not, and you compare them afterwards. If you see a change, it's a little bit better causal argument that the change was due to your treatment. So there's possibly an actively manipulated independent variable. You can determine what that treatment is for the treatment group. There is a control group, and there is pre-post measures, multiple, which is a strong basis for talking about how things have changed. But there's no random assignment to IV levels, and there is some control for extraneous variables, again, trend and seasonality, but also historical things because you got a control group. So it's an okay research design. You can draw conclusions about whether the IV had an effect compared to no treatment, and you control for some history effects and other things, novelty effects. So it's considered an okay research design. So the final one is totally different from all the others. They are single subject reversal designs, and usually it's one person or one classroom where you sort of do a baseline measure, then you have a treatment and you're measuring the dV during each of these, and then you turn it off, you turn it on, you turn it off, and you can kind of go crazy with these. But they're called ABA designs. So there's the BAB design where you have a study group, you have a baseline measure of the dV, then you apply some treatment and measure the dV under that treatment, and then you turn it back off and you see if the dV goes back down again or up again, whatever, returns to baseline. You can keep adding B's and A's, alterations of a baseline versus treatment. So you got a study group again, baseline, measure the dV, you measure the dV during treatment, turn it off, you measure it, turn it back on and measure it. And you're looking for sort of a consistent change associated with the treatment that you predicted. So you can just go nuts. So, I mean, you can do as many BABs as you want. And the more you do, you keep finding that things return to baseline or they change in the direction you wanted during treatment, it does suggest a strong causal argument. So you compare a group or person across alternating dV measurements under baseline and also treatment/event conditions. So for example, you could compare the SSI incidence for a hospital ward across 4 quarters with alternating standard cleaning only versus standard cleaning plus 30 minutes of UV ultraviolet light. And so you would expect that when it's just standard cleaning, the rates would be higher. You start using UVL, it goes down. Then when you turn it back off again and aren't using UVL, it goes back up again. Or you can compare the number of outbursts, for example, for an autistic child under alternating reinforcement and non-reinforcement conditions. And this is kind of where it comes out of, actually. So when you find alternating changes that follow a predictable pattern, it does help make a compelling causal argument for the treatment, right? So this is an okay design, right? The more BABs you do and the more consistent the results are, you can draw conclusions about whether the treatment had an effect compared to no treatment if multiple reversals are demonstrated. So that does it for quasi-experimental designs. Let's talk about true experimental designs. So what are some properties of true experimental designs? They always have actively manipulated IVs. The researcher determines what the levels are. They carefully control the timing and the content of the IV levels to improve construct validity for causal conclusions. They always have a control or comparison group, and they may have pre-post dV measurement as a basis for comparison. So sometimes they have before and after designs as well. The control group helps rule out various threats to internal validity. Having that group is useful. They always have random assignment in true experiments of participants to the IV levels. So it makes it unlikely that the groups are going to differ at the beginning of the study due to things like self-selection bias because you're determining what level they're in. That helps control for confounding by all sorts of known and unknown factors. They have excellent control for extraneous variables and other sources of confounding. So they're pretty good designs. So they help ensure that the only difference between the groups is indeed the IV level because of the random assignment. So you can also control things by holding them constant or including them in the design itself. So how do you assign participants to experimental conditions? Well, there's 3 basic ways to assign them to conditions. There's the between groups design approach where you just do random assignment. You're in that group, you're in the other group in a random way. Within subject designs, you do matched pairs. You pair them up and you randomly assign one to one group and the other one ends up in the other group. And then there's repeated measures designs where you do repeated measures assignment where you assign them to orders of treatments, right? Because in repeated measures design, they're in all levels, so you randomize the order they get treatments. So let's talk about the between groups designs. The random assignment you do is participants are randomly assigned to various conditions so that each one participates in only one level of the IV. It's between groups design. So you assign participants to groups using random assignment. That means they have an equal and independent probability of being assigned to a particular level of the IV. So for example, if you have 2 conditions, you could flip a coin to determine the group to which each participant is assigned. So the reality is we use computers to do this now. They got phone apps even where it picks a random 1 or 2. So if your sample sizes are large enough, random assignment will prevent any systematic biases between your groups and ensure equivalence for both measurable and known variables, so things you know about, social class, IQ, sex, etc. But even more importantly, random assignment takes care of unknown and unmeasurable variables, life experiences, things like that could differ. So the mathematical beauty of random assignment with large samples is that the groups will be similar on all sorts of things you never even considered, and that's why experimental designs are so highly valued. So for within groups designs, you can do matched pairs random assignment. That's like matching, like with the parking ticket writers. So the participants are first matched on some important variable before the pairs are alternately randomly assigned to groups in pairs or clusters. So again, you match them up, randomly assign one person to one group, the other one by default ends up in the other group. So, for example, participants in a memory experiment may be first matched on their IQ test scores before the experiment begins, and that's going to rule out the effects of IQ, right? Because you've equalized the groups on IQ and randomly assigned two people with equivalent IQ scores, one to one group, one to the other. You do that across multiple pairs of people, you end up with equivalent IQ in your two groups, and it rules that out as a confounder. So matching ensures that the groups are equivalent on the variable you matched on prior to their exposure to the independent variable. And matching increases power because it reduces pre-existing differences between the groups. It increases your precision, and it gets rid of noise, really, is what it does, because you've already equalized them on one thing that might have been important. It makes the groups less noisy, more similar to each other from the get-go. So matching is particularly useful when you've got small sample sizes and you need to ensure equality between the groups on some important variables, like age, for example. It's a great way to do that without having to have a big sample. So then for repeated measures designs, remember the participants are in all levels of the IV. So the order of the levels is randomized, or you randomly assign them to counterbalance presentations. So if there's ABC, ACB, BAC, BCA, etc., you randomly assign them to orders of things is another possibility, or randomly assigning them to the levels of the IV in an order that's random is the other way to do it. So for example, in a study of perception of psychologists in the mass media, you have the following three treatments: a negative portrayal of psychologists on a comedy sitcom, a neutral portrayal on a talk show, and a positive portrayal on a drama show. Subjects are going to view all three of these. So you could either use pure random assignment to determine the order they get. So have a computer randomly determine the order of the videos they're going to be watching. Or you can randomly assign them to counterbalance orders of the IV levels. So what you do is you come up with all possible order combos. This is what I was talking about: ABC, ACB, BAC, BCAC, etc. And then you randomly assign participants to those orders in equal numbers. It's another way to do counterbalance random assignment. So one other sort of variation on this is you can always have them get the conditions in the same order, but you have a long enough delay between conditions that you don't have sort of bleed over between conditions. So you make the time interval between the conditions so long that it minimizes the influence of the earlier conditions on subsequent conditions responses. So it is a way to do things in the same order, is just increase the delay between when they receive those conditions. So there are only three major types of experimental designs. There's the post-test-only control group design, the post-test-only multiple groups design, and the pretest-posttest control group design. Let's talk about the first one. So the post-test-only control group design. What's this look like? It's experimental. Start the sample, and you randomly assign, there's not going to be a slash going through it this time, to two conditions, group A, group B. One group gets the treatment, the experimental group. The other group does not. They're a control group. You measure them afterwards. So you got you got post only, and you have one group that's a control group and one group that is the experimental group. So it compares two randomized groups on a single DV measurement after one has experienced the treatment or event. So for example, back to surgical site infection incidents, you can compare between surgery patients who are randomly assigned to recovery rooms that are treated with or without the additional controlled ultraviolet light cleaning protocol. So whether they're randomly assigned to a room that was I mean, they're both going to be clean, but one also has the UVL on top of it or not. So what's cool about the design is you can make absolute statements based on it. That is, you can talk about whether the treatment worked per se versus no treatment. Did this reduce surgical site infections versus no treatment at all? However, there's no way to check whether the randomization actually made the groups equivalent from the get-go. You're randomly assigning, you're assuming that works. And if your sample size is large enough, it will actually, you don't have to have a pre-measure here to say, look, my groups were equal and then they changed. If you have big enough samples and you're using random assignment. This is considered a good design. You can draw conclusions about whether the IV had any effect compared to no treatment at all. So this is one of the standards. The next experimental design is the post-test-only multiple group design. And you start with a sample, random assign, group A, group B. Group A gets treatment level A or experimental level A. Group B also gets an experimental level, so it's not a true control group. It's a multiple groups design where they get a different treatment. And you measure them afterwards to see what effect things had. You know, you do randomly assign, you do have a comparison group, but it's not a true control group that didn't get treated. So you're comparing multiple randomized groups on DV measurements before and after all experienced different treatments or events. So where might you use this? Well, you might compare your surgical site infection incidence between surgery patients who are randomly assigned to recover in rooms treated with 15 or 30 minutes of ultraviolet light, in addition to normal cleaning stuff. So it's both rooms are treated, right, and they're randomly assigned to them, but there is no treatment room. There's no true control. So you can have more than just two. You can have, you know, level C, level D, etc. This is just the example. So the downside of this design is you can only make relative statements. So you can only say how one treatment compared to another, not whether the treatments worked, okay, per se. So that's the downside, is you can just talk about this one. 30 minutes is better than 15, that kind of thing, but not whether it's better than no treatment at all. So again, because there's no pre-measure, there's no way to test whether the randomization actually made the groups equivalent at the start of the study. But again, if you've got a big enough sample size and you're using random assignment, it will work. So this is also considered a good design, but you can only draw conclusions about relative effects, not whether the IV had any effect compared to no treatment. So finally, our third design is the pretest-posttest control group design. Start with a sample, randomly assigned to two groups. You measure the DV before either group gets any sort of treatment. One group gets a treatment, the other group does not, and you measure them after. So you got before and after, and you've got a true control group. This is obviously going to be a strong design. So you're comparing two randomized groups on DV measurements before and after one experienced the treatment or event, the other did not. So for example, if you compare the change in surgical site incidence for patients randomly assigned to different wards in a hospital before and after one ward starts using ultraviolet light equipment as part of a cleaning protocol, the other ward does not. So you could assure the equivalent beforehand. You can talk about change, and you can talk about the effect of ultraviolet light equipment compared to no ultraviolet light equipment. So you can make absolute statements about the based on this design. You can talk about whether the treatment worked per se compared to no treatment. And you can compare the pre-test scores to ensure that, in this case, the surgical site infections were equal beforehand. So if you see a change afterwards, you're pretty darn sure it was due to the ultraviolet light, not some other factors. So this is a great design, actually, but you can draw conclusions about whether the IV had any effect compared to no treatment at all. So it's kind of the best design of all, I think. So how strong, let's sort of apply what you just learned. So how strong of a causal case does this study make for adopting ultraviolet light for reducing surgical site infection incidence in hospitals? So we're going to talk about different ways you might do a study. These are these robot-looking things are the lights that they kick in the room, close the door, they open all the drawers and all the cabinets, and they hit a foot pedal, and they run it for, I don't know, half an hour, and it instead of chemically killing bacteria, it kills them the same way you get skin cancer. It sort of pops their DNA, and they can't reproduce. So a hospital with high surgical site infection incidence incidents purchases ultraviolet light equipment and orders cleaning staff to start using it for their surgery recovery rooms in addition to standard cleaning procedures. So use this in addition to what you normally do. They found that SSI incidence is 30% lower during the 6 months after the ultraviolet light equipment was used. So how strong is this design? Or let's talk about what the flaws are in particular. So they had high incidence from the get-go, and management buys this expensive piece of equipment and puts it in there and says, use this. And so the staff know that they're in a study, right? Or they know they're being watched, right? And so did the rates go down because of the light, or because the staff were sort of heightened in awareness and maybe cleaning better as a result of knowing that management was on their case? You don't know. So, if the rates go down, was it the light, or was it because folks knew they were being watched, like a Hawthorne or novelty effect? So that's the big problem with this study. Maybe they were going down anyway is another problem, and they regression to the mean. They were really high, and things tend to go down anyway. So even if they hadn't bought the machine, maybe the rates would have gone down just because things tend to go towards the average over time. There's lots of potential flaws you can come up with this particular study. So let's look at the next one. Again, SSI incidence during 6 months is compared between California hospitals that are known to have purchased ultraviolet light equipment and those not known to have purchased ultraviolet light equipment from various manufacturers. So you go out and you get the list from the manufacturers, which hospitals bought equipment. And if they are not on a list, you assume they didn't. So hospitals that are known to have purchased ultraviolet light equipment are found to have 30% lower incidence. So what is the flaw with this? The big flaw is they're not randomly assigned, right? So they are choosing to buy the equipment, and what reasons are behind their desire to buy that equipment versus those who did not. And maybe you basically have, maybe the rates were lower from the get-go. Maybe they were 30% lower before they bought the equipment versus not. They're the richer hospitals or something like that. So when you just get this change from self-selected groups, or difference between self-selected groups, you don't know if, first of all, they differed beforehand or not. You don't know if this reduction or lower incidence is even a change, and you definitely don't know that it's due to whether they purchased the equipment or not. It could be other factors as well that you haven't controlled for. So how about this one? They're getting longer. Some hospital surgery recovery rooms are treated with ultraviolet light in addition to standard cleaning, and others are not, depending upon factors such as how busy the hospital was that day and staff availability. And whether patients recover in the ultraviolet light treated rooms or not is supposed to be noted on the medical records by the staff. Changes in surgical site infection incidents during the 6 months before and after the ultraviolet light equipment started being used is compared between patients who were recorded as having recovered in UVL rooms and those without a notation. And the UVL room patients are found to have 30% lower incidence. So the problem with this design is kind of haphazard, like whether they actually went into the rooms that were UVL treated or not was sort of haphazard, depending on sort of how busy things were, whether they actually used it that day or whatnot. Were they using it? I mean, whether they recorded the information about patients, you've got some noise in there, seems like, and so you could have some treatment contamination. And there does not appear to be standardization and procedures for how they were cleaning the rooms. It's not the world's worst sort of way of doing a study, but I think it could be better. So let's take a look at the last one. A hospital's epidemiologist randomly assigned surgery patients to recover in rooms cleaned using standard procedures only, or rooms additionally treated with 30 minutes of ultraviolet light by specially trained staff. Aha! Study staff periodically check that the assignment and cleaning are completed according to study protocol. SSI incidence during the 6 months is compared between patients recovering in the standard or the ultraviolet light rooms, and those recovering in the ultraviolet light rooms are found to have 30% lower incidence. So what makes this design particularly good is there's sort of control, right? They're trying to do a good job of making sure folks were trained, that they were following a standard protocol in the treatment, whether they actually were in the UVL room or not was randomly determined, whether what room they were in, rather than sort of haphazardly by who was available and how busy they were. And so when you see change, you have more confidence that, it probably is due to this 30% reduction is probably due to the treatment rather than other factors. Still not a perfect design, but that's real world research. So I think it's the best one of the four. True experimental design. So that's it on quasi and true experimental designs. If you have any questions, go ahead and put them in the chat and I'll hit them up. Otherwise, good luck.